We've been told to go out on a limb and say something surprising. So I'll try and do that. But I want to start with two things that everyone already knows. And the first one, in fact, is something that has been known for most of recorded history. And that is that the planet Earth, or the solar system, or our environment, or whatever, is uniquely suited to sustain our evolution, or creation as it used to be thought, and our present existence, and most important, our future survival. And nowadays this idea has a dramatic name, Spaceship Earth. And the idea there is that outside the spaceship, the universe is implacably hostile, and inside is all we have, all we depend on, and we only get the one chance. If we mess up our spaceship, we've got nowhere else to go. Now, the second thing that everyone already knows is that, contrary to what was believed for most of human history, human beings are not, in fact, the hub of existence. As Stephen Hawking famously said, we're just a chemical scum on the surface of a typical planet that's in orbit around a typical star, which is on the outskirts of a typical galaxy, and so on. Now, the first of those two things that everyone knows is kind of saying that we're at a very untypical place, it's uniquely suited, and so on. And the second one is saying that we're at a typical place, and especially if you regard these two as deep truths to live by and to inform your life decisions, then they seem a little bit to conflict with each other. But that doesn't prevent them from both being completely false. And they are. So let me start with the second one, typical. Well, is this a typical place? Well, let's look around, look in a random direction, and we see a wall and chemical scum, and that's not typical of the universe at all. All you've got to do is go a few hundred miles in that same direction and look back, and you won't see any walls or chemical scum at all. All you see is a blue planet. And if you go further than that, you'll see the sun, the solar system, and the stars, and so on. But that's still not typical of the universe, because stars come in galaxies. And most places in the universe, a typical place in the universe, is nowhere near any galaxy. So let's go out further till we're outside the galaxy and look back, and yeah, there's the huge galaxy with spiral arms laid out in front of us. And at this point, we've come 100,000 light years from here. But we're still nowhere near a typical place in the universe. To get to a typical place, you've got to go 1,000 times as far as that into intergalactic space. And so what does that look like? What does a typical place in the universe look like? Well, at enormous expense, TED has arranged a high-resolution immersion virtual reality rendering of intergalactic space, the view from intergalactic space. So can we have the lights off, please, so we can see it? Well, not quite perfect. You see, in intergalactic space is completely dark, pitch dark. It's so dark that if you were to be looking at the nearest star to you, and that star were to explode as a supernova, and you were to be staring directly at it at the moment when its light reached you, you still wouldn't be able to see even a glimmer. That's how big and how dark the universe is. And that's despite the fact that a supernova is so bright, so brilliant an event, that it would kill you stone dead at a range of several light years. And yet, from intergalactic space, it's so far away, you wouldn't even see it. It's also very cold out there, less than 3 degrees above absolute zero. And it's very empty. The vacuum there is 1,000,000 times less dense than the highest vacuum that our best technology on Earth can currently create. So that's how different a typical place is from this place. And that is how untypical this place is. So can we have the lights back on, please? Thank you. Now, how do we know about an environment that's so far away and so different and so alien from anything we're used to? Well, the Earth, our environment in the form of us, is creating knowledge. Well, what does that mean? Well, look out even further than we've just been, I mean from here with the telescope, and you'll see things that look like stars. They're called quasars. Quasars originally meant quasi-stellar object, which means things that look a bit like stars. But they're not stars, and we know what they are. Billions of years ago and billions of light years away, the material at the center of a galaxy collapsed towards a supermassive black hole, and then intense magnetic fields directed some of the energy of that gravitational collapse and some of the matter back out in the form of tremendous jets which illuminated lobes with the brilliance of, I think it's 1 trillion suns. Now, the physics of the human brain could hardly be more unlike the physics of such a jet. We couldn't survive for an instant in it. Language breaks down when trying to describe what it would be like in one of those jets. It would be a bit like experiencing a supernova explosion, but at point-blank range and for millions of years at a time. And yet, that jet happened in precisely such a way that billions of years later, on the other side of the universe, some bit of chemical scum could accurately describe and model and predict and explain, above all, there's your reference, what was happening there in reality. The one physical system, the brain, contains an accurate working model of the other, the quasar. Not just a superficial image of it, though it contains that as well, but an explanatory model, embodying the same mathematical relationships and the same causal structure. Now that is knowledge. And if that weren't amazing enough, the faithfulness with which the one structure resembles the other is increasing with time. That is the growth of knowledge. So the laws of physics have this special property, that physical objects, as unlike each other as they could possibly be, can nevertheless embody the same mathematical and causal structure, and to do it more and more so over time. So we are a chemical scum that is different. This chemical scum has universality. Its structure contains, with ever-increasing precision, the structure of everything. This place, and not other places in the universe, is a hub which contains within itself the structural and causal essence of the whole of the rest of physical reality. And so far from being insignificant, the fact that the laws of physics allow this, or even mandate that this can happen, is one of the most important things about the physical world. Now, how does the solar system, in our environment, in the form of us, acquire this special relationship with the rest of the universe? Well, one thing that's true about Stephen Hawking's remark, I mean, it is true, but it's the wrong emphasis. One thing that's true about it is that it doesn't do it with any special physics. There's no special dispensation, no miracles involved. It does it simply with three things that we have here in abundance. One of them is matter, because, well, the growth of knowledge is a form of information processing. Information processing is computation. Computation requires a computer. There's no known way of making a computer without matter. We also need energy to make the computer, and most important, to make the media, in effect, on which we record the knowledge that we discover. And then, thirdly, less tangible, but just as essential for the open-ended creation of knowledge, of explanations, is evidence. Now, our environment is inundated with evidence. We happen to get round to testing, let's say, Newton's law of gravity about 300 years ago. But the evidence that we used to do that was falling down on every square meter of the Earth for billions of years before that, and will continue to fall for billions of years afterwards. And the same is true for all the other sciences. As far as we know, evidence to discover the most fundamental truths of all the sciences is here just for the taking, on our planet. Our location is saturated with evidence and also with matter and energy. Out in intergalactic space, those three prerequisites for the open-ended creation of knowledge are at their lowest possible supply. As I said, it's empty, it's cold, and it's dark out there. Or is it? Now, actually, that's just another parochial misconception. Because imagine a cube out there in intergalactic space, the same size as our home, the solar system. Now, that cube is very empty by human standards, but that still means that it contains over 1 million tons of matter. And 1 million tons is enough to make, say, a self-contained space station on which there's a colony of scientists that are devoted to creating an open-ended stream of knowledge, and so on. Now, it's way beyond present technology to even gather the hydrogen from intergalactic space and form it into other elements and so on. But the thing is, in a comprehensible universe, if something isn't forbidden by the laws of physics, then what could possibly prevent us from doing it other than knowing how? In other words, it's a matter of knowledge, not resources. And the same, well, if we could do that, we'd automatically have an energy supply because this transmutation would be a fusion reactor. And evidence, well, again, it's dark out there to human senses, but all you've got to do is take a telescope, even one of present-day design, look out and you'll see the same galaxies as we do from here. And with a more powerful telescope, you'll be able to see stars and planets in those galaxies. You'll be able to do astrophysics and learn the laws of physics. And locally there, you could build particle accelerators and learn elementary particle physics and chemistry and so on. Probably the hardest science to do would be biology field trips, because it would take several 100 million years to get to the nearest life-bearing planet and back. But I have to tell you, and sorry, Richard, but I never did like biology field trips much. And I think we can just about make do with one every few 100 million years. So, in fact, intergalactic space does contain all the prerequisites for the open-ended creation of knowledge. Any such cube anywhere in the universe could become the same kind of hub that we are, if the knowledge of how to do so were present there. So we're not in a uniquely hospitable place. If intergalactic space is capable of creating an open-ended stream of explanations, then so is almost every other environment, so is the Earth, so is a polluted Earth. And the limiting factor there and here is not resources, because they're plentiful, but knowledge, which is scarce. Now, this cosmic knowledge-based view may, and I think ought to, make us feel very special. But it should also make us feel vulnerable, because it means that without the specific knowledge that's needed to survive the ongoing challenges of the universe, we won't survive them. All it takes is for a supernova to go off a few light years away, and we'll all be dead. Martin Rees has recently written a book about our vulnerability to all sorts of things, from astrophysics to scientific experiments gone wrong, and most importantly to terrorism with weapons of mass destruction. And he thinks that civilization has only a 50% chance of surviving this century. I think he's going to talk about that later in the conference. Now, I don't think that probability is the right category to discuss this issue in. But I do agree with him about this. We can survive, and we can fail to survive. But it depends not on chance, but on whether we create the relevant knowledge in time. The danger is not at all unprecedented. Species go extinct all the time. Civilizations end. The overwhelming majority of all species and all civilizations that have ever existed are now history. And if we want to be the exception to that, then logically, our only hope is to make use of the one feature that distinguishes our species and our civilization from all the others, namely our special relationship with the laws of physics, our ability to create new explanations, new knowledge, to be a hub of existence. So let me now apply this to a current controversy, not because I want to advocate any particular solution, but just to illustrate the kind of thing I mean. The controversy is global warming. Now, I'm a physicist, but I'm not the right kind of physicist. In regard to global warming, I'm just a layman. And the rational thing for a layman to do is to take seriously the prevailing scientific theory. And according to that theory, it's already too late to avoid a disaster, because if it's true that our best option at the moment is to prevent CO2 emissions with something like the Kyoto Protocol, with its constraints on economic activity and its enormous cost of hundreds of billions of dollars or whatever it is, then that is already a disaster by any reasonable measure. And the actions that are advocated are not even purported to solve the problem, merely to postpone it by a little. So it's already too late to avoid it, and it probably has been too late to avoid it ever since before anyone realized the danger. It was probably already too late in the 1970s when the best available scientific theory was telling us that industrial emissions were about to precipitate a new ice age in which billions would die. Now, the lesson of that seems clear to me, and I don't know why it isn't informing public debate. It is that we can't always know. When we know of an impending disaster and how to solve it at a cost less than the cost of the disaster itself, then there's not going to be much argument, really. But no precautions and no precautionary principle can avoid problems that we do not yet foresee. Hence, we need a stance of problem fixing, not just problem avoidance. And it's true that an ounce of prevention equals a pound of cure, but that's only if we know what to prevent. If you've been punched on the nose, then the science of medicine does not consist of teaching you how to avoid punches. If medical science stopped seeking cures and concentrated on prevention only, then it would achieve very little of either. So the world is buzzing at the moment with plans to force reductions in gas emissions at all costs. It ought to be buzzing with plans to reduce the temperature and with plans to live at the higher temperature, and not at all costs, but efficiently and cheaply. And some such plans exist, things like swarms of mirrors in space to deflect the sunlight away and encouraging aquatic organisms to eat more carbon dioxide. At the moment, these things are fringe research. They're not central to the human effort to face this problem or problems in general. And with problems that we are not aware of yet, the ability to put right, not the sheer good luck of avoiding indefinitely, is our only hope, not just of solving problems, but of survival. So, take 2 stone tablets and carve on them. On one of them, carve, "Problems are soluble." And on the other one, carve, "Problems are inevitable." Thank you.